black hole with the mass of our Sun has a temperature of just 60 nanokelvin. Hawking's 1974 paper in Nature calculated this exact figure from quantum field theory. But your own body radiates over 1 billion times more heat than that black hole right now. Hawking stared at his own equations and felt the floor fall away. He had started this work trying to prove his rival wrong, only to discover black holes were slowly bleeding to death. Stephen Hawking, 32 years old, sat in his cramped office at the University of Cambridge's Department of Applied Mathematics and Theoretical Physics. The blackboard behind him was covered in quantum field theory calculations written in his increasingly unsteady hand. He had been wrestling with a problem that seemed to threaten the very foundations of physics, and now, staring at the final page of his derivation, he realized he had just proved something he desperately wanted to be false. The stakes could not have been higher. Classical general relativity, Einstein's masterpiece from 1915, treated black holes as the universe's ultimate prisons. Once anything crossed the event horizon, light, matter, information, it was gone forever. The so-called no-hair theorem stated that black holes possessed only 3 properties: mass, electric charge, and angular momentum. They were featureless, eternal, and completely black. They absorbed everything and emitted nothing. They were the end of the road. But 2 years earlier, in 1972, a young graduate student named Jacob Bekenstein had thrown a grenade into this tidy picture. Working under John Wheeler at Princeton, the same John Wheeler who had coined the term black hole, Bekenstein argued that black holes must have entropy. Entropy, the measure of disorder in a system, always increases according to the second law of thermodynamics. Yet dropping a hot cup of coffee into a black hole seemed to destroy that entropy entirely. Bekenstein's solution was radical. The black hole itself carried entropy proportional to the area of its event horizon. The physics community reacted with hostility. Hawking himself was among the loudest critics. He found Bekenstein's idea physically nonsensical. How could a black hole have entropy without a temperature? And how could it have a temperature without emitting radiation? Black holes don't radiate. That was the entire point. So Hawking set out to destroy Bekenstein's argument with the full force of mathematical rigor. He would prove, once and for all, that black holes could not possess entropy because they could not possess temperature. He combined general relativity with quantum field theory, a marriage nobody had attempted before at the boundary of a black hole. He calculated what happens to quantum fluctuations near the event horizon, where particle-antiparticle pairs constantly pop in and out of existence according to the uncertainty principle, and the math betrayed him. What Hawking found was that one member of each virtual pair could fall into the black hole while the other escaped to infinity. To a distant observer, that escaping particle would appear as real radiation, carrying energy away from the black hole. The black hole, in turn, would lose mass. It would shrink. It would eventually evaporate entirely, vanishing in a final flash after billions or trillions of years. Everything he believed up to this point was wrong. The calculation was inescapable. Black holes had a temperature. They emitted thermal radiation. They obeyed the laws of thermodynamics. Bekenstein had been right all along, and Hawking's own work had gone far further, revealing that black holes were not eternal monuments, but dynamic, living objects with life cycles. They could be born, they could die, and in between, they glowed. Hawking later described the moment as both exhilarating and disturbing. He had forced a unification of gravity and quantum mechanics for the first time in history, but the price was the destruction of a century-old certainty. The universe had just become stranger than anyone had imagined. The winter of 1973-1974 at Cambridge was brutally cold, but Hawking's mind was burning. His body, ravaged by the progression of amyotrophic lateral sclerosis, was betraying him with increasing cruelty. He could no longer write equations by hand with any reliability. His speech was slurring. Yet his cognitive faculties had never been sharper. He was 32 years old, trapped in a failing body, and about to perform the most important calculation of his life. He sat in his office at Silver Street, surrounded by stacks of paper covered in his own scrawled shorthand and, increasingly, the neater handwriting of his graduate students who transcribed his dictated equations. The problem was deceptively simple on the surface. What happens to quantum fields in the violently curved spacetime just outside a black hole's event horizon? Classical general relativity had nothing to say about this. It treated spacetime as a smooth, continuous fabric that bent under mass and energy. But quantum field theory, developed in the 1940s and 1950s by Feynman, Schwinger, and Tomonaga, revealed that empty space is not truly empty. It is a seething foam of virtual particles, particle-antiparticle pairs that pop into existence, live for a fleeting moment dictated by the Heisenberg uncertainty principle, and then annihilate each other back into nothingness. Hawking realized that near the event horizon, something extraordinary happens to this quantum foam. The gravitational field is so intense that it tears these virtual pairs apart. One particle, the one with negative energy, falls into the black hole. The other, with positive energy, escapes to infinity. To an observer far away, that escaping particle appears as real radiation. It is not virtual anymore. It has been given real energy by the gravitational field of the black hole itself. The energy accounting was the most shocking part. The particle that falls into the black hole carries negative energy relative to an outside observer. When it crosses the event horizon, it reduces the black hole's mass by a tiny amount. The escaping particle carries that mass away as energy. From the outside, it looks exactly like the black hole is emitting thermal radiation. It is glowing. Slowly, imperceptibly, it is bleeding mass into the universe. Hawking derived the exact temperature of this radiation, and the formula was devastatingly elegant. The Hawking temperature is given by TWC8EGM-KB, where AI is the reduced Planck constant, c is the speed of light, g is Newton's gravitational constant, m is the black hole's mass, and kb is Boltzmann's constant. The implications are immediate and profound. The temperature is inversely proportional to the mass. A black hole with the mass of our Sun would have a temperature of just 60 nanokelvin, 60 billionths of a degree above absolute zero. It would be essentially frozen, absorbing more energy from the cosmic microwave background than it emits. But a black hole with the mass of a mountain, compressed to the size of a proton, would glow white-hot, radiating at billions of degrees. This was the first unification of general relativity and quantum mechanics in history. Hawking had taken Einstein's smooth, classical spacetime and forced it to confront the quantum foam. The result was not a complete theory of quantum gravity that would take decades and remains unfinished, but it was the first crack in the wall between the two great pillars of modern physics. In 1974, Hawking published his results in the journal Nature, under the deliberately cautious title, Black Hole Explosions. The question mark was not rhetorical. He genuinely could not believe what his own equations were telling him. The paper was only 4 pages long, but those 4 pages would fundamentally alter our understanding of the universe. The Royal Astronomical Society awarded him the Eddington Medal in 1975, recognizing that this discovery had opened an entirely new field of physics. Bekenstein, watching from Princeton, felt a complex mixture of vindication and humility. His entropy proposal had been the seed, but Hawking had grown the tree. The two men, who had started as intellectual adversaries, would later become collaborators and friends. They had together revealed that black holes were not the cold, silent graves the universe had seemed to demand. They were dynamic, thermodynamic objects with life cycles. They could live, and now Hawking had shown they could die. The aftermath of Hawking's discovery was not a moment of triumph. It was the beginning of a nightmare that would haunt theoretical physics for decades. Because Hawking's calculation contained a hidden poison, the radiation he had discovered carried no information about what fell into the black hole. It was purely thermal, featureless, random. A black hole formed from a collapsed star would emit exactly the same radiation as one formed from a billion encyclopedias. All the information about the star's composition, its history, its quantum state, gone. Erased, destroyed. This was not a minor problem. It was an assault on the most sacred principle in all of physics, the conservation of information. In quantum mechanics, information is never lost. It can be scrambled, transformed, hidden, but it cannot be destroyed. The evolution of a quantum state is always unitary, meaning the future uniquely determines the past, and the past uniquely determines the future. Hawking's black holes seemed to break this. They swallowed information and returned only meaningless static. The universe, it appeared, had a memory hole. The conflict came to a head in 1975 at a conference in Dublin. Hawking, now confident in his results, made a bold public statement: information was destroyed in black holes. Quantum mechanics would have to be modified. Kip Thorne, his colleague at Caltech and an expert in general relativity, agreed with him. John Preskill, a young quantum field theorist also at Caltech, disagreed. The three men formalized their disagreement with a bet, a tradition in physics that turns intellectual conflict into something tangible. Thorne and Hawking bet Preskill that information was lost. The stakes were an encyclopedia of the winner's choice, from which the loser could retrieve any information they wished. The irony was not lost on anyone. Leonard Susskind, a physicist at Stanford, watched this unfold with growing alarm. Susskind had built his career on the frontiers of quantum field theory and string theory. He saw Hawking's claim as a direct threat to the very foundations of physics. If information could be destroyed, then causality was broken. The laws of physics became probabilistic in a way that quantum mechanics itself did not permit. Susskind later described his reaction as visceral. He felt like he was watching someone try to burn down the cathedral of physics. He launched a counterattack that would consume the next 3 decades of his career. Susskind's argument was simple in concept, but devastating in its implications. He proposed that the information falling into a black hole was not destroyed, it was stored on the event horizon itself. The black hole, he argued, acts like a hologram. All the three-dimensional information about what falls in is encoded on the two-dimensional surface of the horizon. This became known as the holographic principle, and it was radical. It suggested that the universe itself might be a projection of information stored on a distant boundary. The number of degrees of freedom in any volume of space is not proportional to the volume. It is proportional to the surface area surrounding that volume. For years, this was just a compelling argument. The mathematics to prove it did not exist. Then, in 1997, a young Argentine physicist named Juan Maldacena made a discovery that changed everything. Working at Harvard, Maldacena derived a precise mathematical equivalence between two seemingly unrelated theories: a universe with gravity in 5-dimensional, anti-de Sitter space, and a quantum field theory living on the 4-dimensional boundary of that space. This was the AD-C-Sieft correspondence, a concrete realization of Susskind's holographic principle. It proved, at least in this specific mathematical setting, that gravity and quantum mechanics are dual descriptions of the same reality. A black hole in the bulk space is equivalent to a thermal state on the boundary. The information is never lost. It is encoded in the quantum correlations of the boundary theory. The implications were staggering. If the holographic principle was correct, then Hawking's original calculation was incomplete. He had only looked at one side of the duality. The radiation escaping the black hole was not truly random. It was entangled with the black hole's internal degrees of freedom. Over time, as the black hole evaporated, that entanglement would be transferred to the radiation. An observer with complete knowledge of all the radiation could, in principle, reconstruct everything that fell in. Information was conserved. In 2004, Hawking finally conceded. At a conference in Dublin, the same city where he had made his original claim, he stood before the physics community and admitted he had lost the bet. He presented a new calculation using the ALS-Sieft correspondence that suggested information could escape. He handed Preskill a baseball encyclopedia. But the concession was not clean. Many physicists felt Hawking's new argument was incomplete, that he had not fully explained the mechanism. The bet was settled, but the paradox was not. As of 2026, the black hole information paradox remains one of the deepest unsolved problems in theoretical physics. Recent work has introduced new concepts like quantum entanglement islands and replica wormholes, mathematical structures that suggest information can be recovered from Hawking radiation through subtle, non-local effects. The Page curve, named after Don Page, predicts how the entanglement entropy of the radiation should evolve over time, and recent calculations using the island formula have reproduced this curve exactly. The evidence is mounting that information is conserved, but the full physical mechanism, how information escapes from behind the event horizon, remains a mystery. The deeper question is what this tells us about the nature of reality. If information is truly conserved, then the universe is a deterministic system at the deepest level. Every quantum fluctuation, every random event, every choice you make is recorded in the fabric of space-time. Nothing is ever truly forgotten. The black hole, once the symbol of absolute loss, has become a window into the most profound truth about existence. Information is the fundamental currency of reality. It cannot be created. It cannot be destroyed. It can only be transformed. The paradigm shift that Hawking forced upon physics was not merely a correction to a theory. It was the demolition of a worldview. Before 1974, black holes were cosmic tombstones, permanent scars on the fabric of space-time where matter went to die. After Hawking, they became something far more unsettling. They were engines. They were thermodynamic objects with life cycles, governed by the same laws that describe a cup of coffee cooling in a winter room. A stellar mass black hole, one formed from the collapse of a star perhaps 20 times the mass of our Sun, will take approximately 10 years to evaporate completely. That number is so vast it defies comprehension. It is a 1 followed by 67 zeros, a timescale that dwarfs the current age of the universe by a factor of 10 quintillion. And yet, the math is inexorable. Given enough time, every black hole in existence will radiate away its mass, particle by particle, until nothing remains but a final flash of high-energy gamma rays. This led directly to the formulation of the 4 laws of black hole mechanics, a set of precise mathematical analogies that Bardeen, Carter, and Hawking published in 1973, just before the radiation discovery. The zeroth law states that the surface gravity of a stationary black hole is constant across its event horizon, directly analogous to temperature being constant throughout a body in thermal equilibrium. The first law relates changes in mass to changes in area, angular momentum, and electric charge, the exact thermodynamic equivalent of dETdS plus work terms. The second law, originally proposed by Bekenstein, states that the total area of all event horizons in the universe can never decrease, a perfect mirror of the second law of thermodynamics, where entropy always increases. The third law states that you cannot reduce the surface gravity of a black hole to zero through any finite process, just as you cannot reach absolute zero through any finite thermodynamic process. These are not vague similarities. They are exact mathematical correspondences. The area of a black hole's event horizon is its entropy. The surface gravity is its temperature. Hawking had not just discovered radiation. He had revealed that gravity and thermodynamics are the same language, spoken in different dialects. The quest for a complete theory of quantum gravity now had a non-negotiable requirement. Any candidate theory must reproduce Hawking radiation. String theory, loop quantum gravity, causal dynamical triangulations, every approach to unifying general relativity and quantum mechanics is judged by whether it can derive the Hawking temperature from first principles. As of 2026, string theory has succeeded most dramatically through the Atsi-Seift correspondence, which shows that Hawking radiation emerges naturally from the thermal behavior of a dual quantum field theory. But the deeper mechanism, how space-time itself gives birth to particles at the horizon, remains a subject of intense research. The Hawking effect is the only known physical phenomenon that forces general relativity and quantum mechanics to coexist. It is the crack in the wall between two worlds, and every aspiring theory of everything must pass through it. The philosophical implications cut to the bone. If black holes evaporate completely, what happens to the information contained in the matter that formed them? The conservation of information is not a peripheral assumption in quantum mechanics. It is the central pillar. The wave function of a closed system evolves unitarily, meaning that the final state uniquely determines the initial state, and vice versa. Hawking's original calculations suggested that this unitarity breaks down at the event horizon. The universe, he argued, could forget. This was not just a technical problem for physicists, it was a statement about the nature of time and causality. If information can be destroyed, then the past is not a permanent record. It is a provisional story that can be erased. The arrow of time becomes fragile. Causality becomes a convenience rather than a law. The human story behind this intellectual earthquake is inseparable from the science. Stephen Hawking was diagnosed with amyotrophic lateral sclerosis in 1963 at the age of 21. Doctors gave him 2 years to live. He lived another 55. By 1974, when he published his most important discovery, he could no longer write equations by hand. He dictated his calculations to graduate students, who transcribed them on blackboards while he followed every line with his eyes. His speech was deteriorating. His body was betraying him. And yet, in that failing physical vessel, he produced the most significant theoretical advance in gravity since Einstein published the general theory of relativity in 1915. The discovery of Hawking radiation is not just a scientific achievement, it is a testament to the power of the human mind to transcend its own limitations. Hawking could not walk. He could barely speak, but he saw deeper into the nature of black holes than anyone before him. The final question that Hawking left us is not answered and may never be fully resolved. If black holes have temperature, what other seemingly impossible properties might the cosmos hide? The holographic principle suggests that our entire three-dimensional reality might be a projection of information stored on a distant two-dimensional boundary. The Ad-Sur-CFT correspondence has proven this in a specific mathematical setting, but whether it applies to our universe, which is not anti-de Sitter space, but an expanding, accelerating cosmos, remains unknown. The black hole information paradox has driven 3 decades of the most creative theoretical physics in history. From Susskind's holographic principle to Maldacena's duality to the recent discovery of entanglement islands and replica wormholes, each advance has deepened the mystery rather than resolving it. The universe is not only stranger than we suppose, it is stranger than we can suppose. Hawking taught us that even the darkest objects in the cosmos are not truly dark. They glow, they breathe, they die, and in their death, they may hold the key to the deepest truth about reality, that information is the fundamental currency of existence, that nothing is ever truly lost, and that the past is written in the fabric of space-time itself. Which theory keeps you up at night?